Hi students, here we're going to prove some derivative shortcuts. We're going to prove a number of shortcuts over the next couple videos. The goal here is to see where these things come from. I do not expect you to be able to do these on your own, and that's okay. A good goal would be to get to a place where you could follow along with me doing the math, or you could explain kind of where these steps come from as we do these steps. All right, for the first function we're going to look at, it's going to be a constant. So f of x equals some c. I'm just going to write the definition of derivative at the top of this page. That's the limit as h approaches 0, f of x plus h minus f of x over h. And if the derivative is a constant, I'm just going to go like this. F of x is equal to c. That means that f of x plus h doesn't really matter. That's also equal to c. So if we take the derivative by definition, the limit as h approaches 0 of c minus c over h, what ends up happening is we end up with the limit as h approaches 0 of 0 over h, which is the limit as h approaches 0 of 0. The derivative of a constant is always going to be 0. That means if I ask you to take the derivative of like 2, the answer is going to be 0. The derivative of 4 is going to be 0. The derivative of 14 is going to be 0. Take a second, pause this, and think about why this is true. What shape is that graph? If you said that the shape of a horizontal line is the graph of f of x equals any constant, you'd be correct. And the slope of any horizontal line is going to be 0. That's why the derivative for all constants is going to be 0 as well. All right, for our second one, we've got c times f of x. And that's going to end up giving us kind of a weird thing that we're going to see in a second. So we're looking at the limit as h approaches 0 of c times f of x plus h minus c times f of x. And I'm just going to write over h to save time. I usually write that as x plus h minus x, but just writing that as h is okay. What I'd like you to notice is that we can factor out a c. So we get the limit as h approaches 0 of c times f of x plus h minus f of x over h. And what I'd like us to remember way back when we talked about limit properties is the limit of a constant times stuff. We could write that constant out front. So c times the limit as h approaches 0 of f of x plus h minus f of x over h. And here we have the definition of derivative for f of x. So the derivative of a constant times a function is going to be that constant times the derivative of that function. One of the things that's really important from today and from these videos is that we're building a toolkit of shortcuts so that we don't have to do the derivative by definition all the time. That's a lot of work. And now we have two different derivatives that we don't have to show the definition every single time. All right, here we're adding two functions together. So just to kind of figure out what's going on here, I'm going to do r of x plus h, which when I plug that in, that's going to be f of x plus h plus g of x plus h. In my definition of derivative, which is the limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x minus g of x all over h. What I'd like us to be aware of is that we can rewrite this as two separate fractions. So the limit is h approaches 0 of f of x plus h minus f of x over h. And then to that I'm going to add g of x plus h minus g of x over h. What I'd like you to notice is that we can use a limit property again. We said we had the limit of a sum of two different things was the same as those limits separately. So I could write this as the limit as h approaches 0 of f of x plus h minus f of x over h plus, I'm going to write this down below because I didn't leave myself enough room, the limit as h approaches 0 of g of x plus h minus g of x over h. What I'd like you to notice is that those are the definition of derivative for f of x and g of x respectively. What we can say is that the derivative of what we did at the beginning, which was f of x plus g of x, is equal to what we have over here, f prime of x plus g prime of x. The way that we're going to take a look at this one is to use some algebra shortcuts to come to a conclusion. The algebra shortcut we're going to use is based on this idea, that if I've got something like x to the n minus a to the n, that's the same thing as saying x minus a. It's an a, not a 9. I like how I didn't give myself literally any room here. Oh, this would be fun. I'm going to end up going off the page into the dark space. So we've got x minus a, and that's going to be multiplied by x to the n minus 1 plus a times x to the n minus 2 times, plus a squared times x to the n minus 3, all the way until we get down to a to the n times x to the 0, which just goes away. That's going to come into play when we end up trying to simplify this thing. So we've got the limit as h approaches 0 of f of x, where x to the n. Okay, so we've got x to the n. I like that I totally just wrote that completely invalid in terms of taking the derivative. So we've got x plus h to the n. That's what we're looking for. Minus x to the n. And that's all going to be over h. Okay, here's where this is going to get a little bit weird. So we've got this idea, and where I have x to the n over here, in my derivative function I've got x plus h. Where I've got a to the n, in my derivative function I've got just that x. So what that's going to turn into, it's going to be the limit as h approaches 0 of, I'm going to put that x plus h minus x, that's coming from this part here, out front. And then on the inside, we're going to be left with x plus h to the n minus 1. And then we're going to have plus x times x plus h to the n minus 2 plus all the way down until we have x to the 0 and, that's This is the problem because I use these letters. So it's going to be x plus h to the 0 times x to the n. And I think that should be n minus 1. And that should be n minus 1 over there too. That's my mistake. Okay, we're going to come back to that in just a minute. This is still over h. And you might notice that my x plus h minus x and h on the bottom are going to cancel out. So here's the weird thing that's going to happen here. What we're going to end up doing is plugging in our limit, because now we no longer have the 0 over 0 issue. And we're going to notice something happening. We're going to end up with, for our first part, x plus 0 to the n minus 1, and then x times x plus 0 to the n minus 2. I don't know why I forgot my minus 1 there. Plus, I'm just going to write this all out, x squared times x plus 0 to the n minus 3, and then all the way down until we get just that x left over, which is going to be x to the n minus 1. Okay, so this is going to be x to the n minus 1. X times x to the n minus 2 is x to the n minus 1. And x squared times x to the n minus 3. I'm going to add those powers, and x to the n minus 1. And then I've got my ellipses and an x to the n minus 1 at the end. So all of these end up being the same thing. And the last thing we have to do is figure out how many of them we have. To do that, we're thinking about, okay, we're going from n minus 1 of these down to, I'm going to call this x plus h to the 0. So if we're counting all of these, including the 0th term, we're going to have n minus 1 of them, and then plus 1 more, which is n of them. So what this really is n times x to the n minus 1. This is a really complicated, weird, polynomial factoring-based approach to this. The trick that goes on here is that this is our first actually super useful derivative rule, because this tells us that the derivative of x to the n power is n times x to the n minus 1. We call this the power rule. For example, if I ask you to find the derivative of x to the 7th, instead of having to do this by definition, now that we have a rule for this, we know we can bring that power down front and reduce the power by 1. And that's our derivative. That's a really neat thing. We can also apply this to negative and fractional exponents, although this proof is not good enough for that. To do a proof that fulfills that, we need to know a little bit more calculus first. And in this class, we're not going to do that. We're just going to say that this can be applied to negative and fractional exponents as well.